Look at this point and here. And so they could really see the mass of this object, and they found it's a mass of 3 million solar mass, so extremely massive object. And this passed extremely closely to basically the distance that it passed to the galactic center is just 3 times the distance between the Sun and the Pluto planet. So extremely, on galactic scale, it's extremely close. And so they could find out that there is a huge mass here, which is basically point light, extremely localized. And so the only possibility is that there is a gigantic black hole right at the center of our galaxy. And so now people are studying this black hole at the galactic center. So now what might be surprising to you is the fact that associated with the presence of this black hole, there is so much activity. Because as I said in the standard picture, and I tried to remind you of it, black holes are swallowing everything, swallowing everything. So I remind you that in the theory of general relativity, black holes are singularities of space-time, predicted by the theory. And so there's one point in space-time which is singular, and it is surrounded by what is known as a horizon, and everything that falls below the horizon, so that falls into this sphere, will be falling into the singularity. Everything that means matter, but also light. And because light is also swallowed by the black hole, they are called black holes, precisely. But you have to be careful that this only happens if you fall below this sphere, below this horizon. Otherwise, you could be traveling around the black hole and not be swallowed by the singularity. And so for a long time, this was more like a theorist idea and almost a joke played by Einstein, until people realized that lots of these sources of very energetic particles that we see in the universe are associated with black holes. And I tried to show you in this simulation that the black hole is surrounded by a region of very intense activity. What you will see in this simulation is that, so we start with a galaxy from a distance, it's a spiral galaxy, and then we plunge into it, and at the center of the galaxy there is a black hole. Okay, so this is, we are falling into the spiral galaxy, and right at the center, okay, you have, the black hole is right at the center, and you don't see it very well here because, but there is matter that revolves around the black hole, and really the singularity, if on the black sphere at the center is you have a black hole and its horizon. But just to show you that around the horizon, there are lots of things going on, and what you see here, so you have matter circling around, that's a disk which is accreted around the black hole. And quite often you have also jets of very energetic particles, and that will play the role of a sort of cosmic accelerator. And so indeed, one has found out that quite often one has this structure, okay, right at the center you have a black hole, sometimes a neutron star, but let me take the example of a black hole. So right at the center you have this black hole, its horizon and the singularity, but around the black hole you have a disk, what is called accretion disk, and jets of very relativistic, very energetic particles. And that could be that is found in the universe at very different mass scales. So it could be, the black hole could have a mass of a solar mass typically, or 1 million times the solar mass. The distances could be different, but the same type of phenomena occurs at very different scales. And so until now, all these objects have received different names, and you see, that we call quasar, microquasar, collapsar, and depending on the way you observe them, they could be called blazar or gamma ray burst. There are different phenomena associated to them, but in most cases, you have this very simple structure that people have started in the recent years realize that it's common to these very different objects. Let me just take the example on the right-hand side, which is the example of a gamma ray burst, because that will provide us with an example of what I call a cosmic accelerator. Well, gamma ray bursts are the most luminous events known. They were discovered, the story of their discovery is interesting. They were discovered by an American military satellite whose purpose was to probe the gamma emission due to Soviet nuclear explosions. And they were surprised, maybe they did find some nuclear explosions, but they did find ENVI looking towards the Earth. But the surprise thing was that they also found some big explosions in space. And they kept it secret for, I guess, a few years until they released the information. And so the first satellite was this last satellite, which discovered these huge explosions in space. And here's an example. But you see there is an explosion here, and this explosion is almost sends, in a few seconds, almost as much light as the whole galaxy. And so this is extremely distant. This has nothing to do with, we know now that this is much beyond our galaxy, but still for a few seconds the explosion is so intense that it sends this huge blare of photons towards us. And so, of course, people want to study it because this is a very violent source of energetic particles. It's also because it's very, it sends lots of light. It's very luminous. It can be very distant, and so that would be a way of probing the very distant universe, and so the very old universe. Even, it's even more luminous than supernova explosions. Just to give you a sort of hint of the way these work, let me just show you a simulation, a model for gamma ray bursts, which I think is the standard model nowadays. You'll see the simulation in a second. I just sketch some of the main steps so that you recognize them when you see the little movie. We believe now that gamma ray bursts are due to the explosion of a very massive star which ends its existence with an explosion. Basically, as was said previously, the fuel for stars is nuclear fuel, and at the end of the evolution of a star, the nuclear fuel dies out, and so the star will collapse just because of gravitational interaction. But it's only the inner core of the star that collapses. It releases some energy, and the rest of the star explodes. So you'll see in a second this star, again with our simulation, this star you'll see it from the outside exploding, but on the inside, its inner core is actually undergoing a collapse, and it will be collapsing into a black hole. And this is believed to be one of the ways that black holes are formed in the universe. Well, in some cases, at least the case of a gamma ray burst, one believes that the collapse is not uniform, and as you will see, because it's not uniform, there's a creation, and also because of magnetic fields, there's a creation of jets of particles, very energetic particles. And remember that the outer part of the star has been exploding while the inner core is collapsing. And so the outer part is exploding, and this jet of particles will collide with the outer parts, and there are some particle physics interactions which exactly work as in will accelerate the particles, exactly like in a particle physics accelerator. And so this is what I call a natural cosmic accelerator. So let me show you the simulation in the next. So this is going to go quickly. So this is the star. Okay, so you'll start exploding. So that's what it looks like outside. But in the inner core is collapsing. It's collapsing in a non-uniform way. You have these jets of particles, and these jets will collide with the outer layers, and you'll see that in a second. And this will create some very strong particle acceleration. And so this gives us two jets. And if the beam of light is directed towards the Earth, then you see a gamma ray burst. And this is going to last a few seconds or a few minutes. Well, the main question of, associated with these very energetic particles are how do cosmic accelerators function? I try to give you a model, but of course, you have to check with observation, whether this is reality or, you have to change the model. What can we learn from the study of energetic sources and the laws of physics? The formation of black holes. This is clearly associated with the formation of a black hole. Are there new states of matter at extreme energy or densities? Supernova explosions. This was referred to, by John Ellis. This is also a question that has to do with particle physics, and the formation of heavy elements, which is associated with the explosion of supernovas. Okay, now you have produced with these cosmic accelerators very energetic cosmic particles, then you have to detect them, well, either in space with satellites or on Earth, and there are diverse ways of, that could be at the South Pole, that could be in the sea, that could be in Namibia. There are very diverse ways, very diverse places where you try to study these very energetic cosmic particles, known as, which correspond to the, so in a way it's back to the old, the beginning of particle physics with cosmic rays. We again now study cosmic rays because, they are extremely energetic particles sometimes. And this is what I call a new frontier. There are three different fields which are the art of particle astrophysics, and we present a new window open on the sky. That means that we have observed the sky in photons using light, different wavelengths, X-rays, high energy gamma rays, and so on. But now, particle astrophysics goal is to try to open new windows on the sky, using ultra high energy cosmic rays. I'll say a few words about this. Using high energy neutrinos, and I borrow this title "New Window on the Sky" to this is, if you've ever seen the poster of edited for the Nobel Prize 2002 given to Ray Davis and Koshiba. It was precisely called neutrinos were called a new window open on the sky, and you don't see. I'll come back to this experiment in a second. And the final window, which would be opened in the sky, would be gravitational waves, and I'll just say a few words about each three before concluding. Well, the enigma of extremely high energy cosmic rays. Just imagine that one of these events that I showed you has produced a very energetic particles. This energetic particle will interact with photons of a cosmic microwave background. And it turns out that if it's too energetic, well, it will interact and you'll never see it on Earth. And so one believes, because of this interaction of very energetic particles with the cosmic microwave background, what should not observe on Earth, well, should observe very little, I should say, particles of protons of very high energy, and energy is larger than 5 × 10⁻⁹ electron volts, a huge energy. Well, there are some indications that one observes, particles at higher energies, and that's what these plots, are showing. So there's a question whether, on Earth exists, one can observe, in principle, cosmic rays that are so energetic that they should not be there because they should have interacted with the cosmic microwave background. There is, just to show you an example, there is in Argentina, built by a world collaboration, an observatory where they try to observe these very energetic events. And so they have covered the Argentinian Pampa with these tanks, detectors, 1,600 detectors, which cover an area of 3,000 kilometers squared. Now, why such a large area? It's just because these very high energetic cosmic rays are, when they interact with the atmosphere, are giving a big shower of particles over a very large area. Well, they are still installing some of these tanks, so I'll go through quickly. But the idea is precisely to look at those extremely energetic events, and because they are so energetic, as I said, you have to look at vast areas. Another possibility is not to look at these showers of particles from the ground, but to look from above, and that's another experiment which is planned on the space station, where you would look at them not from the ground, but you look at the atmosphere and try to detect these huge showers of particles. Now, the second window open on the sky are neutrinos, and the previous speakers have mentioned neutrinos. There is a REACH program of neutrino at CERN, and remember that neutrinos are interacting very little with matter. So that's good news for us, because if they come from a very distant cosmic accelerator, they have been interacting very little with the rest of matter, and so they might come all the way to the Earth. Now, the trouble is that they are difficult to observe because they won't interact much with your detector. And so the idea here is to use the whole Earth as a detector, in the sense that you have a distant galaxy here. The neutrino has been traveling a very long distance. And when it encounters the Earth, some of the neutrinos will interact with some of the protons of the Earth, will give a muon, and you detect the muon on the other side of the Earth. And one experiment is called Antares, and those are detectors, particle physics detectors in the sea. And what are interesting are not the particles that come from above, the particles that come from below, because if they come from below, they might have been, their origin might be neutrino coming from a distant galaxy. So just to show you that neutrinos are really interesting because they interact very weakly, but on the other hand, you need the whole Earth to make them interact enough. And the final window open on the sky, new window open on the skies, are gravitational waves. In a way, general relativity tells us that space-time is somewhat elastic. Einstein has told us that when you put a mass or you localize energy, this disturbs space-time and curves it. And so if you have massive objects, that will, just as you disturb the surface of water, if you have an event which implies lots of localized energy, it will curve space-time and propagate along space-time. And so this is, you expect that gravitational waves will propagate in space, and one tries to look for them. One tries to look for them on the ground. We're using ground interferometers. One tries also to look for them in the sky. And this is the LISA mission, which is supposed to be launched in 2012. This is an ESA-NASA mission. And the idea is to look at the geometry of space-time and the possible changes associated with gravitational waves with 3 satellites which are in formation flights. These 3 satellites are at a distance, make a triangle. The distance between 2 satellites is 5 million kilometers. And you shoot laser beams between the 3 satellites in such a way that you try to form a triangle. You fix the distance to the nanometer. So it's really a technological challenge. And by looking at the motion of these 3 satellites in formation, you hope to see, to detect the presence of gravitational waves, which would be due, for example, to a supernova explosion or to the coalescence of two black holes colliding into one another. So this looks like science fiction, but people are working very hard on, on these missions. Now, conclusions. Well, first of all, the new field that the interface between high energy physics and astrophysics has developed in the last 15 or 20 years. cosmology and particle astrophysics provide ways to address fundamental questions which are absolutely complementary to the ones raised in particle physics. I think, the list of questions that I tried to identify are very similar and quite often common to the kind of questions that, particle physics in accelerators raise. There are new windows open on the universe. We still don't know how the universe will look like when you start detecting high-energy neutrinos, gravitational waves, or ultra-energy cosmic rays. And so that might change our understanding of some of the critical issues I was discussing. And particle accelerators such as, the ones at CERN, and especially, those ones, remain the places where one can make experiments. It's exactly what I was saying. The only place where you can make experiments is on Earth. You might get information from the universe, but if you want to repeat something or to prepare something in a specific state, you have to make experiments. And so we might get clues from space, but any confirmation, decisive confirmation, will come, I think, from accelerators. And finally, on a more political side and talking about Europe, this field of particle astrophysics and cosmology is very lucky in Europe, and I would like to stress this point because it is a field that lives in the middle of a triangle, which is formed by, of course, CERN, but two other European agencies, the European Space Agency and the European Southern Observatory. These three international agencies have, of course, already close links. For example, I think it was not mentioned that CERN hosted the ESO headquarters for quite some time. And certainly that gives confidence that, this field will, if it takes its strength from this triangle of three very successful organizations, this field will develop very well in Europe. Thank you.